Hey everyone. So today is Thursday, 5/20, and we're going to be talking about forces on bridges. Okay, so we have a lot of vocab words to go over today, and we'll be talking about the forces on each of the different bridge types. So dead load is the weight of a structure or something unchanging on the structure. So they call it a dead load because it's not moving at all. So an example of a dead load is the weight of the bridge's decking. The decking is the part that like a car would drive across. So some other dead loads are maybe the pillars that are on the bridge, or a fence if the bridge has a fence. Anything that's staying still on a bridge would be part of the dead load. A live load is the opposite. So a live load is anything that's moving on a structure. So the classic example of this would be a car driving across the bridge would be a live load. The reason that we want to differentiate between these two is that it changes the way that we would design a bridge. So if a bridge has a really large dead load and a small live load, that will change the design versus something that has a lot of cars driving across it or a lot of other live loads. As we're thinking about designing our own bridges, you're going to have the live load is a little bit different in this case than in like a normal bridge, because the way that we'll be testing our bridges is just by stacking textbooks on the bridges. So the textbooks won't be moving, but they will be adding up over time. Okay, bridges experience all 5 of the structural forces. Remember, that's what we talked about last week. Tension, torsion, bending, compression, and blanking on the last one. Send me an email if you think of the last one before I do. Usually the biggest forces on a bridge are compression and tension. So we're really going to be focusing on compression and tension in this. And remember, the combination of compression and tension is bending. And there's a lot of bending to think about in bridges, especially in these popsicle stick bridges that we're going to be building. Okay, so we're going to go over each of the major types of bridges and how the different forces interact on those bridges. So in an arch bridge, this is almost all compression force. There's not a ton of tension force in an arch bridge. Basically, if a car or a person is right here in the middle of the bridge, the force from that live load goes outwards and presses against the place where the bridge is grounded. So this is all compression. There's no tension in this image. All right, this is a simple beam bridge with a live load of an elephant. So in this, we're seeing some bending, which means that there is compression on the top. That's those red arrows. So the top part of this bridge is experiencing compression, while the bottom part of the bridge is experiencing tension. So the bottom part is kind of stretching out, while the top part is pushing together, and that's creating that bending force. Beam bridges are really easy to snap, so if you have too much dead or live load right in the middle of that, that's just going to snap. And you can kind of imagine that that would happen in a popsicle stick bridge also if it wasn't strong enough. Either way, I'm going to recommend strongly against making a beam bridge for the bridge project. First of all, it's a little too easy to make that, and it's also just not the strongest version. So the maximum grade that you'll be able to get with a beam bridge would be a B. So just keep that in mind as we're planning. And then suspension bridges are pretty complicated. This would be really tough to build with popsicle sticks. You'd need to figure out some cable material, which we don't really have. If you want to take on that challenge, I'd encourage it, but it will be really, really tricky to figure that out. You can see here, remember, the blue arrows are tension and the red arrows are compression. So each of these posts in the middle, these experience compression. These are pressing down. Whereas the cables are all experiencing tension. They're kind of pulling up the deck and stretching out those cables with the weight of the decking or any cars that are driving across it. Okay, we're going to slightly change directions here because we got to talk a little bit about useful shapes in engineering. So let's point out some shapes that we see in structures. You can pause this video here and just think about the different shapes that you're seeing on these bridges. Okay, so hopefully you noticed there are a lot of triangles around. There's also a bunch of rectangles. In arch bridges, of course, there's that curve, that upside down U, and we're seeing triangles on each one of these. Okay, pause for a second here and sketch what you think will happen to each of these shapes if we apply the force shown in green. So what happens to a square if we press down on it? And let's imagine that that's like a popsicle stick square, if that helps. Or what happens to this diamond that's on a point when we press down on it? Or what happens to a triangle? If you think about it, the triangle is the only shape that won't collapse. The square is, or this rectangle here, is really likely to just kind of slide sideways. The diamond is, first of all, it's not stable on the bottom, but then also it's likely to squish. Whereas the triangle, you'd have to apply a lot of force, and then this triangle would just break rather than kind of squishing like these other shapes. So the point of that is that the angles in a triangle can't change. In other shapes like squares and hexagons, the angles can change, so the shapes are not very strong. In triangles, it will only change shape if it's completely broken. So if you snap a triangle, obviously, then it's no longer a strong shape, but you have to apply a lot of force for that to happen because it won't just slide around. So triangles are the most useful shape for a lot of structural design, and especially bridges as we're thinking about building these. You can also use squares or rectangles and add a diagonal to make multiple triangles. So think about that as you're putting together your popsicle bridge design. Think about how you're going to incorporate strong shapes like triangles. Even if your main shape is a square, like how can you make that square stronger by including a diagonal? All right, and so again, taking a quick look, the reason that all of these have these diagonal lines across these rectangles is to help keep that shape. Okay, that's it for today. Go ahead and fill out the form, and then I will see you in class.